Okay, YouTube, in this video we're going to continue to look at polynomial inequalities, but we're going to look specifically at rational functions having inequalities. And that is to say, like a polynomial over a polynomial, if we make this into an inequality, what would the solutions be? And so considering what we looked at in our last video, basically what we recognize is that this here, this thing that we're comparing to zero, we're saying greater than or equal to zero, this is some function of x or some set of y values here. So really what we're looking for is what values of x on our function cause our y values to end up being greater than or equal to 0. And so what I've done is I've actually went ahead and I sketched this guy, as a matter of fact, without going through all the rigmarole of how to sketch it. What we see here is that we have something that is undefined at -2. And so we have this vertical asymptote here at -2. I could label this here, x equals -2. And then in terms of like zeros, it looks like we have a 0 here at -1. But what I want to note is for what x values is our function having y values that are either equal to 0 or greater than 0. And so when we look at this function here, remember that all y values that are positive are above the x-axis and all y values equal to 0 are on the x-axis. But basically what we could do is we could color in the parts of the graph here that have positive y values, or at least are positive or equal to 0. And so what I get are these two subsections of my graph. So the interesting thing here is, to answer this question, we would say that all x values on this interval here to the left and all x values on this interval here to the right would be solutions to this. And so in terms of writing this, let's talk about a few things. First things first, we could say that this is the interval solutions for where our y values are greater than or equal to 0. We would see that it's all x values starting out at -infinity and going up to, it looks like an x value here of -2, are included in the solution intervals. Now, should I include x equals -2 in the solution interval? And the reason why we do not include -2 is because at -2 our function is undefined. And so in terms of interval here, you notice I wrote an open dot there. I would basically say it's a parenthesis, and we say everything to the left of -2, our function has positive y values. Now looking at the right side, it looks like our function's coming up from the bottom here, hits a 0, and then crosses to being positive y values thereafter. So we would say that all x values that are equal to -1 or to the right are in the solution interval. In this case, we're going to include -1, and the reason why is because we said greater than or equal to 0, and our function is actually equal to 0 there. So one primary difference between polynomial inequalities and, well, rational function polynomial inequalities is that we may include certain endpoints and not other endpoints depending upon not the or equal to that's there or it isn't there, but depending upon whether our function is defined at that x value or not. And so if this is greater than or equal to, yes, we will use inclusion here and use brackets, but if it occurs at a vertical asymptote, then we'll always use an open parenthesis there. So in terms of our solutions that we see here, really the primary question that I have after looking at this little example with the graph is, at which values of x does this graph switch from positive to negative y values or vice versa? And so we could see that, let me color in here. If I were to color in, say, I don't know, how about a green? That's pretty prominent here. Our function is negative for all of these values here. Basically, where did our function switch from being positive to negative or negative to positive? And so what I want you to see is in terms of x values, our function started off as being positive or above the x-axis, but it switched at the vertical asymptote here to being negative. And so in our last videos, we looked at how our function only switches from being negative to positive at zeros like it does here, but we're also seeing that our function can switch from being negative to positive now at a vertical asymptote. And so in terms of where does our function switch from being a negative to positive or positive to negative, we basically want to make a pretty important statement here with rational functions, but we say with rational inequalities. Our function can go from being positive to negative or vice versa at either the zeros of the function, well, either at the zeros of the function, I should say at the zeros of the function, at the zeros of the function, and at the vertical asymptotes. Groovy. So just like in our last video here, we said, well, if we want to solve a polynomial inequality, basically what we need to do is go find all the zeros, okay? And that would give us the intervals of x that we could set up some test values for, or test intervals for. But with rational inequalities, our function can switch at both vertical asymptotes and at zeros here, okay? So with that being said, we're going to have a very similar process when we look at rational functions, but what we're going to have to do is we're going to have to get this equal to 0 first, not equal to 0, but a 0 on one side, but find the zeros of the function and the x values where vertical asymptotes exist. So let's go ahead and take a look at an example where we could deal with this, starting with, well, if you have a rational polynomial here, then what we need to do is factor the top and the bottom, make sure that no common factors exist. So looking at the top here, it seems to me that this factors into x plus 4, x plus 2. And on the bottom here, it looks like we get x. This would have to be a minus 3 and an x plus a 2 here. So what we're going to say is that this polynomial inequality, that it has a removable discontinuity here. As a matter of fact, we end up with a different function. Okay, so this is not the same function as the original. So I'm going to make a note here. Not the same as the original. But it behaves everywhere on the graph the same as on the original, except for at one spot. We say at -2 here. So at -2 on our graph, what I want to make sure we all do is this. We put a big fat open dot right there, because this is actually a point on the graph. If you plug in -2 top and bottom, you're going to get 0 over 0, which is kind of an undefined point. And so we have this hole in our graph, a hole at x equals -2. Okay, so what we want to do is find the zeros of the function and the x values where vertical asymptotes exist. What we're going to know is this. The zeros of the function only occur where the whole thing equals 0. And the only time a fraction equals 0 is if the numerator equals 0. So the zeros of the function are really the zeros of the numerator. Okay. So what we're going to say is, finding the zeros of the numerator, of course, we would set that equal to 0 and solve. We'd say x plus 4 equals 0 if and only if x equals -4 here. So in terms of zeros, let's make sure we list this here. This is one of our critical values. Now in terms of the x values where vertical asymptotes exist, this would be really x values where the bottom is a 0 here. So what we're looking for are the zeros of the denominator. So we say vertical asymptotes occur at the zeros of the denominator. So basically with rational functions, okay, we're going to find the zeros of the bottom and the top, except for we would say that these on the bottom are really where vertical asymptotes exist. And of course, if x minus 3 equals 0, then x equals 3. And this is clearly the vertical asymptote you can see on this graph on the right here. Now, what we're assuming is that most of the time we're not going to have a graph to go off of. And so what we're really going to do is this. We're going to find the zeros of the top and bottom, and we're going to use those to set up our test intervals here. So in terms of test intervals, okay, we would draw out our number line, and we would say that our critical values were at -4, so we say here at -4, and at +3 we have another critical value here. We would say 1, 2, 3, 4, 5. At +3 we have another critical value. So we can see that our graph goes from being positive to negative at -4, and then also goes from being negative to positive at the asymptote. Basically, let's set up our test intervals from this. We would say our test intervals would be from -∞ up to our first critical value, -4. Our next test interval would be from -4 up to the next critical value, 3. And our last test interval would be from 3 out to the right, out to infinity. So just like we've done this before, we need to test this in the original inequality. And the thing here is this. You must test an x value in each of these intervals in the original inequality. So let's pick x values here. I'm going to pick -5 here. I'm going to pick 0 between -4 and 3. And I'll pick a 4 between here and here. But we want to test all of these values. And in the original inequality, what I mean by that is this one right here. Okay, so we have to include the x plus 2 and the x plus 2 there because it's pertinent information. So looking at this, if I were to plug in a -5 into this expression here, basically what I get is I get -5 plus 4, -5 plus 2. On the bottom we would get -5 minus 3, and also -5 plus 2. What we're checking for is whether or not this is less than or equal to 0. And so let's take a look at the values that we get here. -5 plus a +4 is a -1. The bottom line is that it's a negative value. And also -5 plus +2 is a -3, but it is also negative. Down on the bottom here, we certainly get -5 minus 3 is negative, and -5 plus 2 is a negative value. But what we end up with is this on top, some positive value over another positive value. Whenever you have a positive over a positive, you certainly get a positive value here. And so since a positive cannot be less than 0, then this actually fails and we would lose this interval. Now, looking at the graph here, we certainly see that we're looking for all x values that cause our y values to be less than 0 here. Our graph is not less than 0, okay, until it hops over to the other side of this -4 right here. So let's test a value between -4 and 3 and see what we end up with here. And I'm going to kind of block this off here. So plugging in 0, we would get 0 plus 4, 0 plus 2. And this is all over 0 minus 3 and 0 plus 2. But we're saying that we want to know, is this less than 0? Now we can clearly see on the graph here that it is indeed less than 0. Okay, so let's check out the math here to see if we get what we need. 0 plus 4, that's a positive. 0 plus 2, that's a positive. On the bottom, 0 minus 3, that's negative. 0 plus 2, that's a positive. Less than 0. So what we end up with is a positive on top over a negative on bottom, okay? And this means that we end up with a negative, and that's certainly a negative, okay, is less than 0. So since this is true, okay, we're going to keep this interval of values right here. Okay, and then last but not least, we would say we can clearly see that our y values are positive on the right side of this asymptote. But let's say we don't have the graph. What are we going to do? Well, what you got to do is you got to go plug in your representative x value into your function, or at least your factored inequality. So we would say that let's plug 4 in for all of our x's this time. What we get is 4 plus 4, 4 plus 2 on top. On the bottom, we get 4 minus 3, 4 plus 2. We want to know, is this less than 0? And so what we end up with is a positive thing, okay, and another positive thing over a positive thing and a positive thing. And so if you had a positive times a positive, you'd end up with a positive on top. If you had a positive times positive, you get a positive on the bottom. Basically what we get is a positive thing on the left is less than 0, which is a false statement. And so we're going to discount this interval right here. So now in terms of solutions, okay, what we would see is that it's between -4 and 3. Now, we do want to write this, solutions. But the real question is, should I include the -4 or the 3? And so looking at the original, because this is just less than, what we're going to say is that we should just discount both of those and say that it's just going to be parentheses on both sides here. Now, the interesting thing with this graph is that it's actually negative for all x values here, okay, but not at -2 because it is undefined at -2. So I don't throw too many of these out there, but because we have a hole in our graph at -2, hole at x equals -2, then what we're going to do is we're going to split this interval into two separate intervals. We're going to say from -4 to -2, but don't include -2, and we'll start right on the other side of -2 and go up to 3. But that would be this interval right here on the x-axis from here to here and from here to here. Our graph happens to be negative y values there. So with rational inequalities, okay, what we're looking for are the zeros at the top and the bottom, and then going and testing our intervals from there. So let's try this other rational function inequality, and in this case, let's go ahead and start with finding the critical values for this rational inequality. So we definitely want to start by factoring the top and the bottom of this, and so what we get is, I suppose on the top here, x times x plus 3 are our factors. On the bottom, that's a difference of squares, so we get a couple of conjugate factors here, x plus 2, x minus 2. So looking at this, this is our original inequality in factored form. What I want to do is I want to find the zeros of the top, or the zeros of the function, and the values where vertical asymptotes exist, which are the zeros of the denominator. And so let's start with our zeros here. The zeros of the function would be the zeros of the top, and we can see that we would have at x equals 0 a 0, but also at -3 we would have a 0 on our function here. And with respect to the vertical asymptotes, this is the zeros of the denominator, or what would cause this to be undefined. We would see that it's pretty easy to determine. We get plus or minus 2. So with respect to these are our critical values here. What this is going to allow us to do then is to set up our test intervals. Okay, so test intervals. So I'm a big advocate for kind of sketching out the situation here, what we see. But this is our x-axis number line here. And so we want to mark all of our zeros here. So I got 1, 2, 3, 4, 5, 1, 2, 3, 4, -5. Let me mark these in a different color than what we mark our zeros in so I don't mistake them. But our zeros and our vertical asymptotes, we have zeros at 0 and -3, so 0 here, and at -3 we have some zeros of our function. And then at -2 and +2 here we have some asymptotes. And so these would be these parts of our graph here that would have asymptotes that exist on it. Okay. So with these, this will allow us to set up our test intervals here. Because we have 4 critical values, what this means is we're going to get 5 separate intervals. Oh my goodness. So we'd say -infinity up to our first critical value, which was -3. And then also between -3 and 2, okay, -3 and -2, pardon me. And then between -2 and 0, we have a test interval. Between 0 and 2, we have a test interval. And then we would have from 2 out to the right here. And so with these test intervals, what we'll do is we'll select a representative x value from within each interval, and we will plug that back into our original function, original rational inequality. And so to choose values here between -3 and -infinity, I'm going to choose -4, which is the most reasonable value. Between -3 and -2, I'm going to roll with -2.5. Between -2 and 0, why don't we try -1, and between 0 and 2, we'll try +1. And then between 2 and infinity, I'm supposing that 3 would work very well here. So what we're going to do is we're going to test each of these values. I'm going to try to be a little bit more organized on this one here. It's just I have so little room to write in. So for x equals -4, let's go ahead and plug -4 in for all of our x values in this original inequality that we factored. And so we would get this. We would get -4, -4 plus 3, and this would be all over -4 plus 2, -4 minus 2, and this is greater than or equal to 0. So looking at this, I suppose we end up with a negative times a negative on top, and on bottom we get a negative value here times another negative value. Last time I checked, a negative times a negative is certainly a positive, and on the bottom we get another negative times a negative. So we get a positive thing is greater than or equal to 0. What this means is then this is a true statement. And since we get a true statement, we'll put a little box around this interval right here. We say that this interval is going to satisfy this original inequality. Now testing -2.5, one would think that this is a pain in the rear end, but it's actually not if you use the factored form. And the reason why I say this is when we plug this in, we get -2.5 in for x, and then we would get -2.5 plus 3. On the bottom, we're going to get -2.5 plus 2, -2.5 minus 2. And we're just assessing the situation to see if we get a true statement. So here I get a -2.5 times this would be a positive 1/2. The bottom line is that it's positive. The net difference here would be a negative here. -2.5 plus 2 is -1/2. And then this here would give us -4.5, but it's negative. So on top this time, I get a positive times a negative, or in other words, I get a negative. And this is all over negative times a negative, which is a positive. And so because this is a false statement, a negative thing is not greater than or equal to 0, we're going to cross off this interval right here. So let's go ahead and continue to test the rest of these here. When we test -1, suppose we get -1, -1 plus 3, all over -1 plus 2, -1 minus 2, and we'll assess the situation here. So what we get is a negative times a positive on top, and here we would get -1 plus 2 is a positive, -1 minus 2 is a negative. What we end up with then is a negative over a negative, and a negative over a negative is certainly a positive, and so this would be an approved statement. This would be true, and we should keep this interval right here. Okay, so to test 1, x equals 1. We'll test this out here. We say 1, 1 plus 3, okay, 1 plus 2, 1 minus 2, 1 plus 2, 1 minus 2. Is this greater than or equal to 0? So we get a positive times a positive on top. On bottom we get a positive times a negative. And so we get a positive over a negative, which really is a negative thing, and so is not greater than or equal to 0. So we would cross out this interval here, and then the last test we have to run here is just for x equals 3. So I'll try to keep this small to leave ourselves some room to write here, but we get 3, okay, 3 plus 3, all over 3 plus 2, 3 minus 2. So 3 plus 2, 3 minus 2, this is all greater than or equal to 0. What you notice is that we get a positive 3 times a positive 6, or a positive times a positive. Here we get a positive 5, which is positive, times a positive 1. Basically, we get a positive over a positive, which is greater than or equal to 0, which is fantastic. It means that this last interval here also is a solution interval. So here's what I'd like to do. Basically, we're going to write our solutions now, and I hate to spill the beans, but here's our graph that I was going to show us now that we've actually gone through all the work. But we've got some solution intervals here. We say solutions. And what we need to figure out is, are there any endpoints that I should include? Because when I look at this inequality, it wasn't just greater than, but it was greater than or equal to 0. So what I'm going to tell you is, because it's greater than or equal to 0, we will include any endpoints on our intervals here that were also zeros of the function. We would include here because of that, okay? But we will not include our vertical asymptote values because as you look at this function right here at positive and negative 2, our function doesn't even exist. So with these identified intervals that we've gotten here, these three, our first one was negative infinity up to negative 3. When you look at negative 3 here, we can clearly see that this is one of our zeros. And so we wanted to say, well, where's our graph positive or equal to 0? We would say, well, then that's true for all of these x values right here. And so we should include negative 3 because at negative 3, we would be greater than 0 or equal to 0, and we are actually equal to 0 here. So you can see that between, I suppose if I color this part in here, this would be negative between negative 3 and negative 2, and that's why we did not accept this interval because we only want positive y values. We can see that our graph also has, let's go back to the magenta E color here, positive or 0 y values from here to here. So we're going to see that this interval here, this negative 2 to 0, when we write this out, we are not going to include the negative 2 because it was an asymptotic value. But when we go over to this next value here, which is 0, 0 was one of our zeros, and because this was greater than or equal to, we should include the 0. And we can clearly see that on the graph here. We would say all x values between negative 2 and 0, including 0, but not including negative 2. So now for the rest of our graph, we can see that it's clearly positive for everything to the right of this 2 here. That's just this last interval right there. But the question is, should I include 2 as an endpoint? And again, because 2 was an asymptote value, our graph doesn't exist at its asymptotes, we shouldn't include 2. We would just say everything to the right of 2 is going to give us positive y values on this graph. And so this last interval here, okay, that we write in for our solutions is going to be not including 2 and going to the right forever and ever. So you can see that we included negative 3 and we included 0, but those were on our list of zeros up here, whereas we didn't include negative 2 and positive 2 because those endpoints were actually asymptotic.